Okay. Welcome back to the 2025 MIT Paris Symposium. The next speaker is Francesco Cinesta. Francesco is professor of computational physics at Ahemichi Institute of Technology. Francesco is honorary fellow of the Institut Université de France and fellow of the Spanish Royal Academy of Engineering. He led several chairs of Airbus, ESI, Keysight, SKF, and RTE. Francesco will talk about from virtual learning to sustainable action, the central role of hybrid digital twins. Again, please use a Pigeonhole Live for your questions and join me welcoming Francesco to the stage.
Thank you very much. Thank you very much. So first of all, obviously, I would like to thank organizers for inviting me. I will speak about engineering, and in particular, when engineering is helping us to better define and to better operate very complex systems like cities and territories. So I changed a little bit the title. It's Intelligent Modeling for Decision-Making in Critical Urban Systems. So I will speak about a particular project that is called Descartes, that we are developing in Singapore in collaboration with many entities there. One of them is MIT. And we are working in this context with more about 35 million euros budget, and with the Singaporean agencies, as you can see on the bottom, that are obviously the accurate ecosystem in order to develop all this research. So the ecosystem, you can see in this slide, the academic members, the industrial members, the collaborative members, many industries. It's an open project, and there are many of them that are coming during the evolution of the project. We have 3 interdisciplinary programs. We are working in core AI, we are working in engineering, we are working in the interaction between the human and AI, and at the end of the day, we are making demonstrators in order to prove that this technology has sense. So the main protagonist of all this history is the so-called hybrid twin, that I will explain in the next few minutes, because it's the main protagonist of all the activities that we are developing. In fact, you can see from the left to the right, we have data. Data is very important. It's very important in order to operate a system and to model a system that is very complex. Obviously, this data is, we call it smart. The data is like the wine. It's very good, but you need to consume with moderation. If you put 1 million sensors in a bridge, your problem is not the bridge, your problem is your sensors. So, in engineering, data is a delicate topic because data is very expensive. You need devices to collect it, and people in industry know very well the cost of a sensor. You need to communicate this data, IoT, 5G, 6G. You need to store, you need to manipulate before modeling and taking decisions. So, smart data means which data, where, and when. This is the difference between smart and big data. Obviously, you need to decide where you are making measurements. You need to decide the rate of the measurements. You need data no more than needed and no less than needed. And this means, for one application, you need an amount of data. For another, maybe is radically different. But the first point in which artificial intelligence in general cannot help you is in deciding what is the data, what is the nature of data that you need. This is something that is the expert that knows, depending on the problem, which are the valuable data to be collected. You have also on the left, on the bottom, physics knowledge. This is very important. You need physics knowledge means there is a lot of knowledge, and you don't need to learn again fundamental principles, because now artificial intelligence is very timely, and we need to rediscover anything. No, the knowledge that you have is very important because it allows to reduce the amount of data you need. And also this knowledge allows you to certificate and to understand the models that you are constructing. So we have knowledge, this is very important. You have data, this is very important. And for that reason, when we are creating this twin, we are calling it hybrid. Hybrid because it's a combination of knowledge coming from physics, coming from science, coming from engineering science, and we are mixing it with data that we are collecting in the right place at the right moment. Obviously, when you have knowledge, you can predict. We need to predict. Engineering is the science of prediction. We need to predict something in the future. There are many alternatives. You can take a ball of glass. You have the tarot. You can apply this in order to predict. Or if not, you can use science and engineering. But obviously, you make predictions, and you compare the predictions with the data that you collect. And you check if there is a difference. If the difference is 0, this means your model is very good. Why you need data? Why you need artificial intelligence? So you can take your model and you continue making engineering with your model. If the difference is not 0, I call it ignorance. What is the ignorance? The things in the reality that are not in your model. You know all the people coming from academia, coming from industry, that many times no, always, you are predicting something and you are observing another thing. Maybe not too different, but another thing. We are predicting sunny the weekend and it's raining. We are predicting a price or a cost in something is 2 times. So we are making predictions, but the reality is much more than your models. For that reason, in general, there is a deviation between the things that you predict and the things that you observe. And I call it ignorance. So now the problem of the knowledge is solving problems in a computer by making simulation is very expensive. You push the button and you need to wait. And a digital twin is something that should react instantaneously. We have no time. We need to control an asset in real time. And this means knowledge is very good, but in general, when you push the button of the computer, you need to wait. So it's not perfect in order to create a digital twin. On the other side, you have ignorance. And if we have an ignorance, this means we are not predicting accurately the future. And it's there when artificial intelligence, in particular machine learning, is coming, with 2 objectives. The first one is, can we accelerate the predictions coming from the knowledge, the model based on physics? This is called surrogates, a neural network, a decision tree, all the things that exist. This is a state-of-the-art. Take your favorite model. But you can train a regression by using data coming from simulations that are in agreement with your knowledge, with the physics, and now your physics is real time. Wow. I can accelerate the predictions coming from a state-of-the-art physics-based model, and I can operate in real time. This is not a dream, this is possible. And thanks machine learning for making that. Expensive offline, we need to train the model. Online is real time, and this is very important in engineering. On the other side, we are using also machine learning in order to create a model of the ignorance. And you agree with me? If we have a model of the ignorance, and we have a model of the knowledge, we can apply this equation on the top on the right, that I call the fundamental equation of Paco. Paco is my first name. That state, the reality is the things that you know, very good, plus the things that you ignore. And when you put both together, Now you are very accurate and you are real time, fast and well. And this is the first time in the history that we can conciliate fast and well. And this is possible in this hybrid paradigm in which a physics, now real time, that is enriched with the model of the ignorance that we observe with respect to the observations, we can obtain something in which you need few data, because you need only data for the ignorance, only for the ignorance. If your ignorance is quite small, you need few data, and this is excellent. You can understand everything in the physics base, because this is coming from centuries in engineering. So you have a context in which you are making faster, you are making better, you are making cheaper, and you understand. Hybrid twin is the future. So this is the alliance that we are creating on that. So I would like to illustrate how this paradigm works in real applications, in particular for modeling cities and territories. In particular, I will speak a little bit about environment. And in the environment, you have here many videos in which you can see in the image, in the center, in the middle, you can see that depending on the wind today, we are computing the velocity field in any street in the district. This district is Marina Bay in Singapore. There are two small buttons. We can rotate the velocity of the wind, and you can see that the wind map in the district is rotating. This is physics in real time. We have computational fluid dynamics, because in this place there is only 12 meteorological stations in order to measure the wind. In this district, you have few meteorological stations in which you are measuring the wind. So obviously, you are interested in computing and predicting the wind everywhere in the district. Where there is not sensors, you need to put something. And the thing that we are putting there is physics, the Navier-Stokes equations, the computational fluid dynamics. Obviously, you compute the wind in real time. You can, from the traffic emissions, this is on the right on the bottom, we can combine the traffic emissions with the real-time wind map in order to evaluate the air quality in the different streets. In green, the streets in which the quality is very good. In red, the quality is not good. Maybe it's not because there is a lot of traffic, it's simply because there is no wind and the smoke that we are producing remains there. We have other applications in which we have the temperature map, obviously depending on the hour in the day, depending if it's cloudy or not, depending on the wind, we can evaluate again what is the temperature in the district, and we can inform people, we can inform pedestrians, we can inform people that are moving by bicycles what is the trajectory that is the one where the air quality is the best or the one that is the coldest one. We make an application for the Olympic Games in Paris that is called Stay Fresh in Paris. And in this application, you introduce the departure point and the destination point. And the application is proposing you the shortest path, the one in which the temperature is the lowest, and the one in which the air quality is the best. After, obviously, you can choose one or the other. So this is physics in real time, few data, very few data in the order of 10, plus the ones that are coming from the satellite and the meteorological stations, and the other part is physics, and we are combining both in this concept of hybrid modeling. Obviously, we are validating everything. We are validating the thermal comfort. We have data in Singapore. This data is coming from the sensor that we distribute in Singapore. Thanks a lot, MIT, are your material. And we are using this data in order to calibrate our models and in order to validate the models, and the accuracy today is very, very good. In another application that we are developing in Marseille, in that case, they are asking us for simulating in real time for at a given velocity state, the velocity and the angle when there is a fire, how this fire is evolving. We are simulating this in almost real time because the wind map is ready and the model for the propagation is ready, and we are providing this predictor to the fireman in order to plan the mitigation conditions or in order to operate to better manage this crisis. We can use also, in order to make planning, this is in urbanism, you could try to change conditions. For example, when you are planning a new district, you can change the location of the buildings, the height of the buildings, and in real time, you can evaluate what are the environmental conditions. As I mentioned at the beginning, one engineer is making two things. The first one is planning, and the second one is operating. Operating is natural. This is for planning. This is a digital twin. It's not real data, it's historical data. This is generative AI, if you want, because obviously this is something that we are using in order to better plan a district in the city. We are applying this also in indoor environments. And again, we are applying this kind of technology in order to apply this hybrid concept. You can see on the top on the left, this is the CFD. We have the physics-based model temperature, and we have again these thermometers. Thanks again, MIT, are coming from you. We are measuring the temperature, and we can see that the temperature that we are measuring is very close to the physics-based model. There is 1 degree of difference. It's not too much. But the idea is, the difference is called the ignorance. Why there is a difference? Because probably the reality is a little bit more complex than the model that we establish. And in that case, we can create a model of the ignorance that if we add to the physics-based model, we have the predictions of the hybrid one. And as expected, the predictions of the hybrid one are more or less the reality because I construct a surrogate of the gap, a surrogate of the ignorance, and not a surrogate of everything. There are many things that you know. Please take the things that you know. You don't renounce the things that you know because every day, today, everybody is speaking about AI. Take all your knowledge, as if it's not perfect, enrich your knowledge. But you don't need to learn again things that are today quite solid. We visited the moon. We come back from the moon. No data. No artificial intelligence. So this means our physics is not so bad. We have models that predict quite well. Maybe we can make better. Oh, yes, we can make better. 1 degree better. In that case, we create a model for the 1 degree better. But it's not necessary to reinvent all the engineering and all the science because now there are tools for, I don't know, like in the computers, Intel inside, stupid outside. So take care of that. And obviously, as soon as this is there are many technologies today in order to experience this. We can experience this in augmented reality. This is one of the demos. You have a reduced model of Marina Bay. We are using drones for many applications. And the important thing is coming in few seconds. You choose, because you would like to fly from one point to another, and you would like to determine the optimal trajectory in order to reduce the consumption. As soon as you make the decision, the wind is there, we are computing the optimal trajectories in real time, and this is deploying the drone in these very small drones, and the virtual coupled with the real, and you can see now the streamlines that day of the wind, how the drone is flying. At a certain moment, the wind changes, and when the wind changes, is more or less now, we recompute the new trajectory in order to continue to be optimal. We can also superpose the turbulence zones. It's in the rear part of the buildings. You cannot fly there because there is a lot of turbulence, and you can obtain and visualize this in real time. This is coming from the data that we send to the model, very few, and from physics. You can see in blue, this is the regions in which there is a lot of smoke. There are emissions, but And here you can see what is the temperature at the level of the buildings for a given velocity wind, for a given position of the sun. So this is in order to prove 10 data plus physics is making something that is very good, that is being validated by the agencies, the governmental agencies in Singapore, and is quite well. In order to show you the resolution, this is also coming from Google State. So you can see we have a very nice texture. You can ask, I would like to see the temperature in this range, and you can superpose the temperature. You can visualize this in the MetaQuest. This is immersive virtual reality, but with textures that are very, very good. And now for a wind condition, you can change in real time because we compute the wind map for any condition, for any velocity, any direction. And now, obviously, you can move there, and you can see that with an excellent resolution, you can evaluate the conditions today, and you can evaluate many scenarios, for example, in the future. Remote sensing, you can see the image, the most important one that is on the right, on the top. What is this? We have infrastructures, and instead of putting 1 million sensors in the infrastructure, we are using a drone. The drone is flying, you have a camera, and you can observe for example, a pipe in order to detect a crack impacts, but you can put also acoustic devices, thermography, or even ultrasounds. And you can see, sorry, I come back. You can see we learn by using artificial intelligence and simulation the state of the material. You have the drone is flying, and as soon as there is an impact, we can superpose the state of the material. And obviously, it's not necessary that the operator is there. The operator could be in the office. You have your HoloLens. You are visualizing the same thing that the drone, but we are introducing or superposing to this image, we are superposing the image or the solution that is coming from physics. So this is real-time structural health monitoring, and this is remote because you are in your office, the drone is flying, and you are observing the state of the material. If everything is good, you continue, but if one day you discover corrosion or you discover a crack, you have a predictive model in order to evaluate the remaining useful lives. Drone trajectory planning, not necessary to speak about that. Emergency crisis, I think, is the same. Many maritime applications, maybe 1 or 2 for the environment. Probably I will finish with these ones. I don't know if they are working. You can see on the right, on the top, is not working the videos. Can you make something, please? Yes, please, excellent. So maybe we are finishing with this. This is something that was requested by the Maritime Port Authority in Singapore. You have all the ships in the port. You know the wind conditions today. There is a vessel that has an emergency. In that case, we are predicting an emission of ammonia. This is very dangerous. If this is coming to the city, in 1 minute you are dead. And obviously, as soon as we identify the position of the mission, as we know the velocity wind in real time, there are many, many views, but it's important to see this is exactly the velocity at which we are computing the evolution of the polluant when it's coming to the district. There are many views. This is obviously, again, physics in real time with field data, the order of 10. You can evaluate what is the part of the district that is impacted by this emission. But the important point is, and if tomorrow the wind changes, and this is coming in few seconds, again, another view of the arrival of the pollution to the district, but the important thing is coming in few seconds. Now the wind is 75 degrees orientation, and now we are changing the conditions, it's moving to 45, and the important point is, in real time, I can continue evaluating the impact of the pollution in the city. This is important because in case of emergencies, the authorities could take decisions, could simulate millions of scenarios in order to take the best decision, or we could imagine also making applications to inform people about the risk. Maybe to finish, if you can, yes, this one is nice. The one on the bottom, this is the same, but we change wind by currents. This is the port of Singapore. And please check physics in real time. We can move the source of the pollution, and in real time we can evaluate what is the dispersion and what is the part in the port that is impacted by that. So this is more or less, I finish with that. The main idea is take your physics and speed your physics by using machine learning. Very important. Now, if your physics is not good, because you are predicting something, and you are using a drone, and you see that the things that you predict are not exactly the things that you observe, no problem at all. Take the difference and create a model of the difference only, add this to the predictions, and you have an hybrid twin that, again, faster, better, cheaper, and you understand. Thank you very much.
Thank you, Francesco. So I will go through some questions here. Which algorithms do you use for finding the optimal trajectory?
This is very good. Why? Because the drone, what is flying, we take into account the wind, because obviously we try to minimize the consumption, and we need to choose the trajectory that minimizes the resistance. So the wind is very important. Second, I try to never fly in the zones in which the turbulence is very high. And now, as soon as you have this, that is a cost function, in the cost function there is all the consumption, and a penalty in order to never penetrate in the regions that you cannot penetrate. Now the problem is a problem of optimization. There are people that directly use rain for learning. Why not? The problem is you need to train. Other people coming from our generation, schools of engineering, at least in France, we are very close to something that is called the Euler-Lagrange equations. So finally, we are making the optimization. We are using the Euler-Lagrange equations, and obviously the cost function is a neural network because it's very nonlinear, and the trajectory that is a very nonlinear function depending on the drag, the wind, etc. This is another neural network. But it's incredible. I compute the optimal trajectory without any data coming from experience.
Okay, the next question is, what about the generalization of your model? Are the cities than Singapore, are the forest?
For other cities?
Other cities or other forest?
Yeah. The things that we are developing in Singapore, obviously, this is very good because these guys are paying. But the technology should generalize. And this means all the things that we develop in Singapore, we apply also, in particular in France, we analyze all the districts in Paris, La Défense district. How generalize? The procedure is exactly the same. The procedure that I put in my slide describing how the digital twin or hybrid twin applies is absolutely agnostic. So this means you can apply in one city, you can apply in the other. You need to solve some cases for different scenarios on the wind in order to construct the surrogate or your physics, and you need some data in order to check if there is a difference, and in that case you create a surrogate of the difference. But obviously everything is absolutely agnostic, and this means we apply for the cities, but not only, we apply in industry, in manufacturing, in health for humans, or we can apply this, in particular, I think is there. In Renault, we apply a lot of hybrid twins for the many systems, many complex systems in the car.
Okay. How do you validate if you have only few sensors to measure?
Yes. In order to validate, first, we have the sensors, we construct the model, we make the model of the difference, and after these sensors or other, I need to move in order to make the validation. In particular in Singapore, I cannot validate in the streets of Singapore. I cannot put a sensor in a street in Singapore. We are working with the governmental agencies that as soon as I provide my predictions, they put sensors in some places. In particular, there are LiDARs that are now running in the city For 1 year, they are collecting data, and they are comparing the data that they collect with the predictions coming from us.
Okay.
So validation is absolutely important, because if not, you know, CFD, this is computational fluid dynamics, also is translated like color for directors. Colors is very good, but we need to validate.
So we have one more question.
Perfect.
It has 2 votes. What is the room for POMDP, partially observable Markov decision process, coupled with digital twins in decision-making and planning in subsurface modeling, such as in mining and geothermal?
Yeah. When we take into account all the uncertainty that we have in the media, in the boundary conditions, in the model itself, we are using absolutely, in order to take into account the uncertainty, Markov processes, and we are creating distributions that are in agreement with the distribution that we consider as a prior, and from that, we are computing the optimal choices in the system.
Okay, thank you, Francis.
Thank you very much.
I feel high energy from Francesco just standing next to him. Okay? So next session is a fireside chat moderated by Vincent Marais, Group Bouygues Innovation and Transformation Director.